Okay, we start with rates of change. This is the first topic of our syllabus, average rate of change, instantaneous rate of change. And we will solve an exercise about the average rate of change in the first example. Okay, before we solve it, I want to remind you the geometric meaning of the average rate of change. Let me put a recall here before we start. Okay. So a recall here about the average rate of change and its geometric meaning. So this is a Cartesian coordinate. Let me draw a function here like that. For example, let's name it as f of x. And let's choose 2 points on our curve. Let's say this is x0 point, and let's say this is the point x1. And let's also indicate their images as f of x1 and f of x0 and f of x1. This is y-axis, this is x-axis. Now, how do we compute the average rate of change of a given function over a given interval? Do you remember how we do that? Okay, before remembering this, let me lead you some geometric discussion. Let's connect these 2 points by a line, okay? Sorry. So we can connect these 2 points with this line, right? So this line is called as a secant line. If you remember from the lecture videos, this green line is a secant line that connects 2 points on our curve. Now, we will consider the slope of this secant line. How do you compute the slope of it? How do you compute the slope of it? You need to compute the lengths of these sides of this right triangle, right? The slope of this secant line, slope of this secant line. Let's find an expression for it. Okay, so the length of this side is the difference of these 2 images, right? So I will write there like, okay, f of x1 minus f of x0. F of x1 minus f of x0 divided by this length, which is given by x1 minus x0. This is obviously the slope of this green secant line here. And it is in fact the same as the average rate of change of the given function over this given interval from x0 to x1. So this is the geometric meaning of the average rate of change of our function. Average rate of change of f of x, average of something is always computed over an interval, right? So average rate of change of f of x over the given interval. So our interval is here from x0 to x1. That's why I will write here over x0, x1 closed interval. So this is what I want to recall from the lecture videos to you. Average rate of change is computed by this ratio and it has a geometric meaning. It is the slope of this spatial secant line on our curve. After this reminding, now we can concentrate on the first example. A function is given, g of t is 2 plus cosine t. We want to compute the average rate of change of it over this given interval in part A. So average rate of change of f of x over the given interval 0 pi. We know how to compute it. We just remember it here. We will use the endpoints of our interval images divided by the difference of them. So I will take the difference of the images. I know the x1 and x0 points, so I can write it like f of, not f, but g. Our function is given as g of pi minus g of 0 divided by pi minus 0. This is at the same time the the slope of the secant line. Okay, let's compute the image now. G of t is given like that. We will just insert pi for t. So this is 2 plus cosine pi, and this image is 2 plus plus cosine 0. How do we compute cosine pi? If you don't remember cosine pi directly, you can get help from unit circle. So let's draw a unit circle here, which will help us to read values of certain trigonometric functions. Okay, let's concentrate on this point on it. So this point has x and y components. So what is that point in Cartesian system? So this is a unit circle, means that its radius is 1. So this point corresponds to 0, minus 1, 0 point. And this point, if you measure the angle starting from x-axis, corresponds to pi measure. So this is how you use unit circle to measure the values of certain trigonometric angles. The x component gives you cosine value of this angle, and the y component 0 gives you the sine value of that angle. Okay, so cosine pi is minus 1 from the unit circle. By looking at the unit circle, you understand that cosine pi is measured as minus 1. What is cosine 0? This time you concentrate on this point. This point is 1, 0. So this shows you 1 is cosine 0 and 0 is sine 0. So cosine 0 is 1. Okay? So here we have 2 minus 1 minus 2 minus 1 divided by. So the result is minus 2 over pi. This is a real number, and this real number is the average rate of change of the given function g of x over the given interval 0, pi. Okay? Any questions about this solution? Okay, so let me move on. Today, I want to talk more about on limits, computing limits of given functions. So we are given a graph here, and by looking at this graph, we will answer these true-false questions. Okay, let me first try to explain what does this notation mean. Limit of a function f of x as x goes to 0. To find out what this limit is as x goes to 0, you will approach on x-axis to 0 from both sides first. So x approaches the 0 from both sides. When this happens, what happens when you approach 0 from both sides? What happens to the images of your function? Is there a unique real number towards which these images are approaching? So look at the graph. As x approaches 0 from both sides, then you follow the graph, follow the images of your graph. So these are the images, right, on y-axis, and they are approaching towards which real number? So what is the answer here? The values of f function are approaching to 0, okay? So, sorry, this limit exists, this is true, and the value of this limit is 0, as we can verify from the graph by following the images on your graph. They are approaching to the value 0 as x approaches 0 from both sides. So this is also true. True. This is obviously false, as we just explained that this limit is 0. Now let's concentrate on another point as x goes to 1. Okay, this time we will search for 1. Here is the point 1. Now I will approach to 1 from both sides on x-axis. This notation means that. And while approaching 1 from both sides, look at the graph. On the left side, the values are approaching towards which real number? I need some answers from you. So
minus 1.
Okay, thank you. So on the left side, the images are approaching to minus 1. Now let's look at the right side. On the right, I follow the graph and I see that the values on the right are approaching to which real number?
0.
0. So since the left limit and the right limit are different, if there is a limit, if this limit exists, it has to be unique, okay? If limit exists, it has to be unique. Don't forget this. You cannot have two different limits on two different sides. Since this is the case here, on one side, the values are approaching to -1. On right side, the values are approaching to 0. That's why there is no unique number towards which your images are approaching. So limit of this function as x goes to 1 is not 1. In such cases, we say that limit does not exist, okay? And also it is not 0, limit does not exist. Because on the right side and on the left side, the images are approaching two different values. Okay, now in part F, we will concentrate on the interval -1 to 1. So now we will look at all the values on this interval. Let's choose some arbitrary point x0, which is inside this interval. Let's say x0 point is here, okay? Now we will search for the limit as x goes to x0, as you can see here. So x goes to x0, x goes to x0 from both sides. Then let's follow the images. The images on the graph are approaching to where? They are both approaching to, let's say this real number is L, they are both approaching to L, right? There is no problem on both sides. The images are approaching to the same real value L. This means that limit exists or not?
Exist.
Limit exists and its value is L. And this is true for all the x0 points in this interval. No matter where you choose your x0, the same situation happens, right? No matter where you choose your x0, right-hand side and left-hand side, the images are approaching towards the same image on y-axis. This is because this graph over -1 to 1 of your function is a nice graph. There is no holes, there is no breaks, there is no jumps. That's why the images are approaching to the same value from both directions. So for all x0s in this interval, limit exists. This is true. And let's look at x equals 1. Again, it says as x goes to 1, this limit does not exist, where we already answered here, because right-hand side and left-hand side, left-hand side limiting points are different, so limit does not exist. This is already true, as we answered above. Okay, so any questions about this solution? This is an exercise where we see the graph of the function and we read all the limiting information. When you have the graph, it is not that difficult to find out the limiting values because you will just follow the graph as you approach your number from some certain side. Okay, if no questions, I want to move on. Okay, second exercise. This is also a nice exercise too. This time we don't have a graph. What we have is some information about the function. By using the given information, we will try to solve a puzzle kind of question. So the given information is this one. Limit of our function as x goes to 1 is 5. So then the question is, must f be defined at the number 1, at the real value 1? Must f be defined? To have a limit as 5, as x goes to 1, does your function has to be 1? I'm sorry, has to be defined. So let me draw a graph and you will understand. Let's say your function behaves like this. Let's say this is a point 1, and you see I am trying to make our function satisfy this given information here. So what is the limit of this graph as x goes to 1? You see, if you follow the graph as x approaches from 1 from both directions, you see that the limit is what?
5.
5. Okay, this is satisfied. Now we can answer the question. Must f be defined at x equals 1? Is it defined here?
No.
f of 1 is not defined, but still it has this limit as 5. So the answer to this question is a big no. It doesn't need to be defined to have the limit as x goes to 1 as 5, right? There is no dot here, it's a hole. Our function is not defined here, but still it has a limit. Okay, let's continue. If it is defined, must it be 5? Must it be defined as 5? Let's also answer this. Now I want to define the image of 1 somehow without violating this limit information. Should I define it as 1? This is the question. Should I?
No.
No, I don't need to, because I can put this dot not here to here, for example, and it won't violate limit being 5, right? Let's say this point is 10. Now, I defined f at 1 as 10, but still, this limit information is valid. Still, limit of our function as x goes to 1 is 5. So, f1, what was the question? So, f1 doesn't need to be defined as 5. f1 does not need to be defined as 5, okay? As you can see my graph, I choose f1 as 10 and still it has the limit as 5 as x goes to 1. Okay, so the answer to this question is also a big no. Can we conclude anything about the values of f at x equals 1? Okay, can we say anything about the definition of this function f at x equals 1? This question is about where to put this dot. I can also put that dot to here, for example, here or here, and it won't violate the fact that limit is still 5, right? So we cannot conclude anything about the value of 1 for this function. So I will put this explanation like we can define it as any number we wish, right? You can put this dot anywhere you like. You will still have limit as 5, okay? That's why we cannot conclude anything about the value of f. It can be anything. This is also a big no, which is explained here. Is that okay? Any questions?
No, teacher.
Okay, so this was part A. Now we will look at part B. Part B is pretty much the same concept, but thinking from the reverse direction, you will see. Okay, let's put part B here. Now, we don't have the limit information, but what we are given is f1 is 5. And we want to understand the limit, just in the reverse direction we did above. So if f1 is 5, can we say anything about the limit of it? Let's try to answer this question. Let me draw a graph for you. Let's say like that. I put a jump here, okay? We want that f1 is 5, right? f1 is 5. That's why I put this dot here. f1 is defined as 5. Okay, what about the limit? Limit of this function as x goes to 1 is, what is it?
Does not exist.
It does not exist. Thank you for the reply, because let's say this is 8, for example, because if you follow the graph from left and right side, you see that their values, the images are approaching to different values, 5 and 8, because there is a jump here. Because I put this jump here, there is no unique number towards which your values are approaching as x approaches to 1 from both directions. So this limit does not exist. f1 is 5, but limit does not exist. That's why I need to say no to this question. f1 can be still 5 without having a limit there. Okay, next. If it does, If limit exists, then must it be 5? Now let's answer this question. If limit exists, if f1 is 5, must the limit be 5? What do you think?
No, teacher.
Yes or no? Yes, the answer is no, thank you, because your situation may be, for example, like this one, right? Okay, I want to define f1 as 5. You see, I defined it 5. Look at the limit. What is the limit here?
Limit is 3.
Exactly, f1 is 5, and limit of f of x as x goes to 1, if you follow the values, you understand that it is 3. You see, I can still have f1 5, but limit doesn't need to be 5. Limit does not need to be 5. It can be any number like 3. Or I can force it to be any real number by playing with the graph, right? Or I can define it like this so that it is now -7. Why not, right? So can we conclude anything about the limit? What do you say? As I told you, we can force the limit can be any real value by playing with the graph like this. So we cannot conclude anything about the limit. Okay, so limit can be forced to be any real number. That's why we cannot conclude anything about the limit. There is also a big no here. Okay, so I think this is a very nice question that helps you to understand the limit concept, the value of the function, do they have to be the same or not, and so on. Okay, do you have any questions about this solution?
No, teacher. Thank you.
Okay, thank you for your reply. Now, we studied the limit concept geometrically so far. Let's try to find the limit algebraically without having the graph, and instead of having the graph, we have this explicit expression for the function. Okay, when you try to insert x equals -3, what happens to your values? For the denominator, if you insert x equals -3, you obtain 0. Also for the denominator, if you insert -3, you will obtain 0 too. What is 0 over 0? What do you think? So 0 over 0, infinity over infinity, 0 times infinity. What do you think about these forms in calculus course? Also infinity minus infinity. This is not 0, this is not 1. Similarly, not 0, not 1, not 0, not infinite, not 0. We call these things as indeterminate forms in math. Indeterminate forms, okay? Which means we don't know the result of them. Okay, they have a result, but they are hidden. You cannot directly conclude this is equal 1, for example, because it is not. So the result of this thing is hidden. Somehow we need to get rid of this indeterminate form to obtain the result. How can you do that? There are several ways to get rid of indeterminate forms. For example, you can, if you have polynomial over polynomial, the first thing you need to try is to decompose the polynomials. So there is nothing to decompose at the denominator, but at the denominator, you can rewrite this polynomial like that. You can decompose it like this. So then you start having this simplification, and then you end up with more simplified form like that. Okay, we are looking at the limit as x goes to -3. Now we are safe to insert -3 to our expression, which gives us the result as -1 over 2. Okay, this is one way to get rid of indeterminate form, as I said, decomposing polynomials. Now, let's look at the next case. This time we don't have polynomial over polynomial. instead we have a square root function, let's try to insert h goes to 0. If you insert h equals 0 here, numerator becomes 0, denominator becomes 0. So this is an indeterminate form, which means that we need to work harder to get rid of this indeterminate form. And there is no decomposition here as we had in the previous example. Instead, we will use another way, which I call as multiplying and dividing by the conjugate of that expression. What do I mean? Okay, let me rewrite the question. This is what we have. So the conjugate of the expression in the denominator, conjugate means it is almost the same expression except this sign, okay? Instead of writing minus, I put plus. So I call this as the conjugate of this expression. So I multiplied by it, then I need to directly divide by it because I don't want to change the question, right? Now, another recall. I'm sure all of you will remember this decomposition form. A minus b, a plus b. So it is a squared minus b squared. This is a very famous high school information. And let's look at our case. Let's say this is a, this is b, this is a. Sorry, this is b. So we have exactly this form here, right? A minus b, a plus b, and I am trying to multiply them. And this is a quick way of multiplying them. So what we have at the denominator is a squared, which is this expression, minus b squared, which is this. And then I will write the whole thing at the denominator. Don't forget to write this, please, because it is already there. And then these fours are simplified. After simplifying them, you can also simplify h's. So what do we have then after doing all such simplifications? As h goes to 0, 5 over 5h plus 4 plus 2. Now we are safe to insert h equals 0 because it doesn't cause any problem anymore. So the result is 5 over 4. Okay? This is another way of dealing with indeterminate forms when your function includes square roots. Then you will multiply and divide by the conjugate of the square root to have simplifications like this. After simplifying, you can easily insert your number to obtain your result. Okay? So let's move on. This time, okay, first of all, you need to understand whether it is an indeterminate form or not. So I will insert 0 to understand the value of it. Sine 0 divided by 3 times cosine 0. Remember, sine 0 was 0, cosine 0 was 1. We read these trigonometric values on the unit circle above. So what is the result? We have 1 plus 0 is 1. And at the denominator, we have just 3. You see, this is the most perfect case ever where you have no problems with inserting the value and you obtain the result without any kind of problem. So this is the easiest case ever you may run into. Sometimes life is that easy, but not always, as it is here. Okay, look at this one. If you insert x goes to 2, what happens? Okay, 2 squared 4, 4 plus 12, 16, square root 16 is 4, 4 minus 4 is 0, and denominator. You obtain an indeterminate form. So we learned what to do for such cases. We will divide and multiply by the conjugate of this expression where I just changed the sign of it. Since I multiplied by it, I need to divide by it too, not to change the question like this. Then, as x goes to 0, this is a minus b, a plus b form. You know, that's why I will quickly multiply them as a squared. This is a squared minus b squared, right? Like this, x squared plus 12 plus 4. So what do we have? X goes to 2. This is x squared minus 4, and in the denominator, nothing to do. X squared plus 4 can be decomposed, right? It can be decomposed. Wait, I forgot to write this thing, right? You should warn me about such mistakes. So x minus 2 is already there, and also this one then. X minus 2 and then square root thing here. Okay, maybe I should write like this. X squared plus 12 square root plus 4. Okay, now I was decomposing that like this. X minus 2 and square root of x squared plus 12 plus 4. Okay, now I am ready to simplify. This helps me to get rid of this 0 over 0 indeterminate form. Then I will be safe to insert my number. Insert x equals 2, please. 2 plus 2 divided by 2 squared plus 12 plus 4. So the result is 4 over 8, which is 1 over 2. Okay? So this is an example of how you need to treat this indeterminate form if you have square root functions in your expression. You need to multiply and divide by the conjugate of it. Okay, any questions on this one? Okay.
No, teacher.
Let me move on. The next exercise, which will be an easy one, is about the limit laws that I mentioned in the recorded video. Limit can be distributed over sums. Limit can be distributed over products, and limit can be distributed over ratios. There is a ratio here, okay? Provided that as long as the last one has some condition. You can distribute limit over ratios if the limit of the denominator function is not 0. There is just one condition in the ratio part. Okay, we are given informations about limits of p of x as x goes to minus 2. It is 4. Limit of r of x is 0, and limit of s of x is given as minus 3. So now we can first distribute this limit like this one. Limit as x goes to minus 2, r of x, limit goes to minus 2, s of x. You see, I distributed over sum, the limit operation. And then what you need to do is to use this information. Limit of p of x is 4, r of x is 0, s of x is minus 3, so the result is 1. Now, similarly, you can distribute limit over products. P of x, limit as x goes to minus 2, r of x, times limit as x goes to minus 2, f of x. So result is 4 times 0 times minus 3, 0. And in the last case, okay, we will distribute the limit, but be careful. Provided that the limit of the denominator is not 0, you can distribute it. And it is given as minus 3, we are safe, we can distribute it. Limit of the numerator, limit of the denominator, okay? In the numerator, we have minus 4p plus 5r x function. By the way, there is also this nice property of limit. After distributing limit to, okay, let me do it step by step. Now, for the numerator, you will distribute limit over sum, right? So I will write two different limits for the denominator now. This is limit of s of x is at the denominator, limit of minus 4p plus limit of 5r. And this property is also nice. You can take constants out from the limit operation so that you have minus 4 times limit p plus 5 times limit r divided by limit of s. Now we are ready to give the result. Minus 4 times limit of p function, which is 4, limit of r function is 0, limit of s function is minus 3. Okay, so if you insert these values, you will obtain the result as 4 minus 0. Of course, there are coefficients there. Sorry, let me also put the coefficients. Okay, so The result is minus 4 times 4, 5 times 0 divided by minus 3. Okay? So this exercise, it explains you how to use limit laws. Limit distributes over sum over products. You can take constants out from the limit operation, and you can distribute limit operation to ratios as long as you don't, the limit for the denominator is not 0. Okay, any questions? Then let me move on. Now, this is a very important part, one-sided limits. After solving this first part, we will take a 15 minutes break. So look at the graph. We are given a graph again. This time, what does one-sided limit mean? Okay, one-sided limits. Now, we will be putting this extra notation to our limit notation, plus or minus. Plus means, okay, let's start solving the example. As x goes to minus 1, plus. This plus means that you are approaching minus 1 from right direction. Minus means, if it would be minus, we would say that we are approaching from left. Plus means right, minus means left. Okay, so if you approach minus 1 from right, what is the limit of this function? All you need to do is to follow the graph, right? So what happens to the values of this function if you approach minus 1 from right like that? The values are approaching to which number? The values of the graph are approaching to, look at the images. You see the images are approaching to some certain real number. What is that?
1.
On y-axis, yes. This limit is 1. This is true. We verified it from the graph. Okay, let's look at 0 now. We want to approach 0 from left direction. Then follow the images. They are approaching to which real number? 0. That's why this limit should be 0, not 1. This is false. And let's also look at this one from right. Okay, this time we will approach 0 from right. Then what happens on the graph? The images are approaching towards 0 again. That's
0.
Why exactly. Left-hand side limit is 0. Right-hand side limit is 0. They are equal. So this is true. And if one-sided limits are equal, then you conclude that if they are the same, then you say that limit of your function without putting plus or minus, the overall limit, exists and it has this same value. Okay? So limit of f of x as x goes to 0 exists. This is true because left-hand side and right-hand side limits are the same as 0, then limit exists. So what is this limit? It is not 1, it has to be 0. So this is false. By the way, we looked at the limit from left here. We already confirmed that it is 0. This is also true. Okay, now let's look at as x goes to 1. Okay, as x goes to 1, does this limit exist? To understand that, we need to look at one-sided limits. Okay, x goes to 1 from left. What is this limit? Limit of this function as x goes to 1 from left. How do you answer this question? You will follow these images. What is the limit on the left?
It's 1.
It's 1. Then let's look at the right-hand side limit. Limit of f of x as x goes to 1 from right. Follow your graph. Your graph is constant. It always gets 0 value. So this limit is 0. And now compare them. Since they are not the same, they are not the same. That's why, what can you say about overall limit?
Limit does not exist.
Yes, if one-sided limits are not the same, you conclude that limit does not exist. Okay? So this limit is not 0. In fact, it does not exist. This is false. And okay, it is not 0. It is not 1. We already showed that this limit does not exist. False. What about This one, this limit exists 0. Yes, this is true. We already concluded it here. Now let's look at as x goes to 2 from left. Okay, x goes to 2 from left. Now we are here. What is this limit? Your function is a constant function. Here it always gets the value 0. So limit of your function as x goes to 2 from left is not 2 but
0.
0. So this is false. What about from the other direction, right? Okay, now we are looking at this direction from right. What do you think? From this direction, where is the graph? Is there any graph on the right side of 2?
No.
No, there is no graph here. Over this side, f of x is not defined, meaning that there is no graph. That's why you cannot talk about the limit here. Even your function is not defined there. So you will conclude that right-hand side limit of course does not exist because there is no graph there, okay? So this is obviously not 0, does not exist. And let's look at -1 from left. The same situation happens here. From left direction, there is no graph. Saying the same thing, f of x is not defined. That's why from left direction, limit of your function as x goes to -1 from left is what? No graph, not defined, so you cannot talk about the limit. It does not exist. This time it is given as true. Okay? So this is how you read one-sided limits from the graph. Once you see the graph in front of you, finding the one-sided limits are in fact not that difficult. You will just follow the images on your graph. That's all. If left-hand side and right-hand side limits are equal, just like in this case, then you conclude that the overall limit exists and it will get the same value as here. This is the most important thing that we use here. Okay, maybe I can put a recall about that, then we can take the break. Okay, what is the most important recall that you need from the lecture videos here? Limit of your function as x goes to some number from right. If this is the same as the limit of your function as x goes to a from left, if they are the same, let's say, as the real number L, then the conclusion about the overall limit is your function f of x has the limit as x goes to a as L. It exists and it will be the same number L here, okay? This is the importance of one-sided limits. We want them to be the same for our function to have a limit as the same values. Okay, any questions about this part?
No, teacher.
Okay, then I stop sharing my screen. Let's take 15 minutes break, okay? See you after the break.